I'm Bamsago. I'm a master student from KAIST, and today I'd like to talk about how to detect sandboxes to prevent sandbox frauds on the network using cellular capabilities. This is a joint work with Junho, Sanguk, Minchar, Yonghwa, Professors Minsak, and my advisor Yongdae. Let me start. A sandbox is a VoIP gateway that converts voice over IP calls to cellular calls and vice versa. It also contains multiple SIM slots, baseband chipsets, and antennas, so it enables to make multiple calls simultaneously with a single device. And because of these characteristics, SIM boxes can be legally used in call centers, but it is also often illegally used by criminal activities. So first, SIM boxes are often used for interconnect bypass frauds. Interconnect bypass fraud is one type of fraud that fraudulent carriers bypass interconnection agreements between the carriers and operators. By using SIM boxes, fraudulent carriers can convert routed internet calls to local calls and ultimately cause a revenue loss of network operators. According to a recent survey, this fraud caused a revenue loss of about $3.11 billion worldwide in 2021. And second, SIM boxes are also used in voice phishing, which is also called as voice scam frauds. Voice phishing is another type of fraud in which fraudsters deceive victims to obtain their money or personal information. For this, they impersonate close people of victims, such as colleagues or family members, and sometimes government officials such as police officers. By using SIM boxes, the fraudsters can stay outside of the legal boundary of the victim's country. My home country, South Korea, got a financial loss of about $600 million in 2021. To prevent such SIM box frauds and detect SIM boxes, a few previous studies attempt to detect SIM box or SIM box calls. Pindrop and Boxed Out presented SIM box call detection using the voice call quality, while several other works presented SIM box detection using call detail records. However, these techniques can only detect SIM box or SIM box calls after the calls are made, so the frauds cannot be prevented. Then, how about using IMEI for SIM box detection? IMEI is a 15-digit identifier allocated to every cellular devices. As each allocated value is unique, IMEI enables identification of individual cellular devices on the network, and it can be used for banning stolen or malicious devices. The first 8 digits of IMEI is also called a TAC, and it represents device models. The right table shows some examples of TACs of some smartphone models. And so one might think that SIM boxes can be detected by MNOs on the network if they can maintain a proper database of IMEIs and TACs. But unfortunately, this does not work. And this is because of the limitations that IMEI have. First, IMEI is a device-reported value with no validation process. And because of this, once the device reports IMEI to the network should trust it because it has no validation process. And therefore, even though the malicious UE reports false IMEI, network cannot detect it, and so such malicious devices cannot be detected by IMEI. And moreover, we observed that commercial SIM boxes support IMEI manipulation. As shown in the below figure, IMEI of SIM box can be easily changed by only entering a new IMEI that fraudsters want on the red right table. So IMEI is not sufficient for detecting SIM boxes. Then, can we detect SIM box without using IMEI? Here's our intuition. Every year, 3GPP adds new cellular capabilities to their specification. In the same time, baseband manufacturers produce new chipsets with new capabilities which is added to the new standard. And also, smartphone manufacturers produce new smartphones with new chipsets, thus new smartphones contain new capabilities. But meanwhile, most IoT devices, including SIM boxes, do not use high-end chipset. So what do we mean? It means that SIM boxes may be fingerprint SIM boxes and smartphones may be fingerprintable using the cellular capabilities. For example, as shown in this table, you can see that Galaxy S9, S10, and SIMBox support different cellular capabilities. And based on this intuition, we attempt to fingerprint device models by using the cellular capabilities. And to generate the fingerprints using the capabilities, we utilize two cellular control plane messages, which are used to report cellular capabilities. And those messages are called NAS attach request and RRC UE capability information. And note that these messages are used for all cellular devices to report their capabilities. NAS attach requests contain various features such as support of various security algorithms and support of some network technologies like handover. And RRC UE capability information contains features about the radio connection information, such as support of specific bands. Even though we attempt to use these messages to construct the fingerprint, we cannot directly use them because of the two considerations. The first consideration is that end users' customization affect cellular capabilities. For example, if we configure the device to only use LTE, all 3G and 5G algorithms are disabled in the device, and the device reports their capability without 3G and 5G algorithms. Just like in this example, if we do not consider the effects of end users' customization on capabilities, we cannot generate a proper device model fingerprint. In this work, we consider two ways to configure the device by using Settings tab and Engineering mode. And by using these two methods, we could find a table of configurations that actually affect cellular capability of devices, as you can see in the below table. And to consider the effects, we set the devices to each configuration when we collect the messages to generate fingerprints. And the second consideration is to prune the features that should not be used for fingerprinting. And this is because some features are not device model specific, which means that they do not represent device models, and thus they should not be used for fingerprint. The goal of the pruning is to generate a filter, as you can see in the bottom, through two types of analysis, which consist of the features that are not device model specific. And due to the time constraints, I'll only introduce specification analysis in this presentation. And the goal of the specification analysis is to find the features that meet three properties, which are user-specific, session-specific, and related with previous connections. User-specific features, for example, are the features that are related to the user itself rather than device models, so they are not useful for generating device model fingerprints. And those include user identities, which surely vary by different user, not the different device models. And to find those features, we analyzed 4 cellular specification documents in total. And as a result of the specification analysis and intramodal analysis, we could build a filter and generate the proper device model fingerprint. And for the study on the fingerprints, we utilized 102 individual cellular device models, which include 85 smartphones, 11 IoT devices, and 6 SIM boxes. With the generated fingerprints, the first thing we could discover is that most smartphones have unique fingerprints. Under the default configuration, 83 out of 85 smartphones have unique fingerprints, and only 8 pairs of smartphones have overlapping fingerprints, even though we consider all configurations. And more interestingly, we could find that those exceptions can be considered as the same device models because all of those pairs have same device models and they are built from the same device manufacturers, and also they are released almost at the same time. You can see the list of the exceptions, which is called cohorts in this work, in the right table. So from this discovery, we could confirm that fingerprints can be used to distinguish smartphone models. And we also made further analysis to investigate the factors that contribute to the uniqueness of fingerprints. And as a result, we could find that baseband vendors and phone vendors highly contribute to the uniqueness of fingerprints. First, baseband vendors often employ their unique configurations to several technologies. For example, they use different configurations on battery-saving technique called DRX, and they also and only some baseband models from some baseband vendors support the positioning technology. And also in case of phone vendors, they can also choose to support some of the capabilities. So this implies that phone vendors can also contribute to the uniqueness on the fingerprints. And so from this study, we could confirm that different baseband vendors and phone vendors make unique fingerprints. And lastly, we could find that smartphones and SIM boxes actually have different fingerprints due to the two major differences. The first difference is that carrier aggregation-related features only appear on the smartphones. And this is because of the hardware limitation on SIM boxes, because SIM boxes only have a single antenna for each baseband chipset. They cannot support CA while smartphones can. And also, SIM boxes do not support features that are related with recent protocol versions. And this is because SIM boxes use low-cost baseband chipsets, thus their supporting protocol versions are relatively low compared with the smartphones. So we can conclude that fingerprints can be used to distinguish smartphone models and SIM boxes. But however, we also observe that IoT devices and SIM boxes might have overlapping fingerprints if they use same baseband model. And because of this, SIM boxes and IoT devices might have overlapping fingerprints, and that's why we presented access control list, which is a suggested network behavior to ban SIM boxes on the real network. In our work, we proposed this access control list that utilizes a reported IMEI, a fingerprint, and a subscribe plan to make a decision to whether accept or reject the device, which is initially attaching to the network. And we showed that most SIM boxes can be banned with no false positive and initial false accepts, assuming that MNO only allows voice service to the registered IoT devices. And please check more details for this in our paper. And in conclusion, I presented how to detect SIM boxes using cellular capabilities on the network. And also, we are currently in discussion with a Tier 1 MNO in Korea to test and deploy this technology. And from the discussions, we could also find that some false positives can be reduced by using call detail records or call patterns, or use SIM card types with the fingerprints we generated. And lastly, this is a part of a large project from a Korean police to fight with the $600 million crime. And we're developing some practical solutions to fight with this crime.